Hi guys, so we are back with the third segment of chapter 4 lectures, and we're going to start from slide number 22 as promised. And we're going to start discussion on relative motion. Now this is slightly, at first this is quite simple, and then suddenly when you are going to actually start working on examples or solving problems, you're going to see that some of these relative motion problems could be really tricky if you do not remember or understand the basic definitions, okay? So just be attentive and be careful when we are defining the notations, because that will carry a lot of weight at the end. So just the figure, this figure tells you, right? If we have, let me use the spotlight. So if we have like 3 to 4 different moving objects, there are 3, looks like I can't count. Anyway, so you have Amy, Carlos, and then Bill inside the car. They're moving differently. So Amy is at rest, right? So if you wanted to attach a velocity with Amy or speed with Amy, you can say this is like v equals to 0. Then you have 5 meters per second, then you have 15 meters per second, okay? Now, if you are a bystander, if you are like a person at rest, right, standing somewhere here, then you would be able to tell that Amy has 0 velocity, Carlos has 5 meters per second, and Bill with the car has 15 meters per second. Basically, this is what we have been doing so far when we solved problems regarding initial velocity and final velocities, or basically what we have been working with absolute velocities, okay? So these numbers 0, 5, or 15, these are absolute velocities, and absolute velocities are only valid when you have like a reference frame, or when you have a reference point which is a static point of reference, okay? So imagine or remember, we always pretty much wanted to have an origin, right? Pretty much somewhere here. And then if you wanted to specify displacement, you can use the coordinates. For example, x coordinates of these guys are this, right? And then you can use the initial and final positions to find out average velocities. Very simple, along x-axis, of course. We are not even talking about anything along y-axis. However, and then it would basically simply tell you that Amy has a 0 average velocity because the initial position and the final position are the same. Carlos will be here initially, but then at some point Carlos will probably be here, and then you can take this length and then divide by the time interval, and you'll probably get this number. Same with Bill, right? Maybe initially he's here, and then finally he's probably somewhere here, and then you take that length, divide by time, you get Bill's average velocity. But we're not talking about these absolute velocities. We are basically now interested to know what are the velocities with respect of these guys with respect to each other, okay? So how Carlos is going to perceive the velocity or the motion of Amy or the motion of Bill. How Bill is going to, what Bill is going to see when he is looking at a static person like Amy, or another person who is moving slightly slowly, or a lot slowly, let's say, depends on which scenario you're looking at, and what Bill is going to see or perceive, okay? So this perception of velocity, the perceived velocities are going to be different from the absolute velocities. And you can see these examples all the time in your everyday lives, right? So if you are driving on a highway or generally on any like road, and you have a person standing, let's say in a bus stop or just anywhere along the road, then eventually you're going to see that that person will actually move opposite to the direction that you are moving. So if you're moving from left to right, what Bill is going to see that Amy is actually moving from right to left. And similarly, Bill is going to see Carlos is also moving from right to left, but with a slightly slower velocity with respect to Amy. So all these perceptions are going to come into place if you think about relative motion. And that's the thing that we are trying to deal here. Okay, so what are the motion, or what kind of perception we are going to get when we look from one moving reference point or reference frame to another. All right, so for that we are going to use some conventional notations. So for example, if we are trying to tell like Carlos's velocity with respect to or according to Amy, meaning what Amy is going to see when she's looking at this moving bicycle, right, is CA. Okay, so the first one is the person or the object of which you are specifying the velocity, right? So you are looking at Carlos's velocity, so C comes first, and then the next alphabet, the next symbol that you're writing comes from who is watching. So in this case, Amy is watching, so your velocity is going to be called as VCA. If you already know that we're talking about X direction, you can say it is VXCA, okay? Similarly, VXCB will be the velocity of Carlos with respect to Bill, right? So, and again, you can see that Carlos is moving forward or moving to the positive X direction. That's why the relative velocity of Carlos with respect to or according to Amy is a positive number. The velocity of Carlos with respect to Bill or according to Bill is a negative number, because according to Bill, Carlos is not moving forward. Carlos is actually moving backward with respect to this car. That's what he is going to see. And again, there is nothing absolute about it. Is Carlos actually moving to the left, or is Amy actually moving to the left? They are not, but it is a perceived vision. It is this perception that we are trying to say. And this perception is important, okay? Because if you want to be in one reference frame, and if you are trying to describe the motion of another object, which is in another reference frame, then this technique is going to be inevitable to be used. You cannot compare absolute velocities from one reference frame to another if they are not in the same reference frame, okay? You will have to establish a relationship between them, and then only you will be able to understand what this guy is actually doing. All right, so every velocity is measured relative to a certain observer. We have been always using relative velocities, but we have been actually anchoring the origin right at where Amy is standing, okay? So a static reference point, which is our origin, and that's why we have been calling them as these velocities as absolute velocities, but there is no true velocity, so to sense, okay? So we have been working with absolute relative velocities all the time. We have just made it easy by putting one of the objects or one of the person or one of the reference point, generally speaking, to be at rest. So moving forward, here is a generalized equation that you are going to use, okay? So if you want to find out velocity of Carlos with respect to Bill, or according to Bill, you can basically write the velocity of Carlos in this fashion. So you can write velocity of Carlos with respect to any other person. And in this case, you can take Amy, for example. And then if you bring in the velocity of Amy with respect to Bill, you will get by. You will basically, without directly knowing CB, you can find CB by this rule, this chain rule, okay? The inner subscriptions cancel. The outer subscriptions basically define what you are finding. So if you are given a problem and if you have a freedom to play with this equation, like by all means use it. And in some problems, there will not be any other way to find the relative velocity of one person or one object with respect to another without going through this chain rule. Okay, so there is the second rule that is very important as well, which is basically the opposite rule. If B is moving to the right relative to A is moving to the left relative to B. So if you know one of the relative velocities, you can flip the sign, and you will know the relative velocity of the other. So if you know velocity of B with respect to A, you can add a negative sign in front of it, or you can multiply that number with a -1, and now you just know the velocity of A with respect to B. So these rules are very handy when you are solving relative motion problems. But again, what we are trying to do here is we are trying to arrive to a set of rules or a set of techniques which would be handy when you are, as I said, when you are basically sitting in one reference frame and you're trying to describe the reference frame, an object from another reference frame, okay? So Amy and Bill are in two different kind of reference frames. Amy is in a reference frame which is a static one, right? So Amy is static. Amy describes all the motion the very similar way we have been doing from chapter 1, 2, and 3. We have never bothered about the relative motion until this point because we were gauging or we were measuring all the displacements, velocities, and accelerations like Amy. So everything looked like true velocities, but of course there's nothing like true velocities in real life, right? It's all relative. So now if we want to know what Bill is going to see when Bill is looking at Carlos, then we will actually have to understand the relationship between these two different reference frames, okay? And if we are talking about displacements, you can like just use the tip-to-tail law to understand that the position vector of Amy according to Bill or A with respect to B. Now we can drop the names and simply use the alphabets or the symbols, right? So this is our A position vector of A with respect to B, right? If you want to find position vector of C with respect to B, this will be our CB, and it will be this vector, right? And now if you want to know what is our CA, right? If you want to know what is the position vector of C with respect to A, this is this vector. And if you look at this triangle you just drew, right? And you can see that these two are basically going in both anti-clockwise direction, right? So it's giving you a sense of anti-clockwise motion. However, this guy is going from the opposite side. So you can form a relationship between these three vectors, right? And it will look like our AB plus our CA equals to our CB, right? And that's exactly what you got here. So now suddenly you have found a relationship that connects the position vector of C from B and from B and from A, okay? So you have two reference frames, but you can know the position vector from one, if you know the position vector from the other, and how these two reference frames are related with each other. And that's very important. I mean, eventually we are going to basically drop all of these reference frame drawings, but we are going to work with these relations, these expressions that you're seeing right here. And once you know the displacement, you can work with velocities very well, right? So you can just simply take derivative of these r's, right? So this is like dr dt, dr dt, dr dt, but then we will have different suffix. So eventually they will look like velocities if you take differentiation from both sides from the previous equation. And once you do that, you will basically arrive at what we all know as Galilean transformation of velocity. Excuse me, Galilean transformation of velocity. So we have established not only the position, but also the velocity transformations, right? So if you now know one velocity with respect to a certain reference point, you can find the other velocity or the same velocity from a different reference point if you know the relationship between these two coordinate systems or reference frames. And remember, you need two separate reference frames only when one of them is moving with respect to the other. You don't need this relationship when you work with like two separate static reference frames, okay? So if Amy and Bill, from our example, they were both static or they were both moving similarly, right, in the same car, then the reference, you would not need a new relationship to establish how C is perceived from these two people, because then it will just be the same thing or a constant addition to them. It's not complicated in those scenarios. It's only valid or it's only required, let's say, when you have one of them, A and B, is moving with respect to each other. And now you have another person or another object that is moving, makes things very complicated. So only then you need this equation to work with. Our final topic is circular motion, and it's actually not the final topic. It has several subtopics with it. So we are going to go through a part of circular motion and associated uniform and non-uniform acceleration with it, and then eventually we're going to stop and probably make a very short final version or final part of the video. We'll see how it goes. I may actually go ahead and complete everything in this segment. I may just stop. So consider a ball on a roulette wheel, right? So what you see here is basically an object that is at a certain point of time, at a certain space, in two-dimensional space, right? However, it is changing in a very interesting fashion. It is rotating. And when it rotates along a circle, it gives us several interesting or intriguing characteristics. So for example, if an object like that roulette wheel, the ball in the roulette wheel, basically, if it is moving very regularly or uniformly on a circle, we call it uniform circular motion. And by uniform circular motion, just like uniform linear motion, we are saying that the speed at each of the points is the same, okay? Now, there are several important information you need to take out from this slide. Number one is, if you are at any point, if you are on this circle, okay, you basically have obliged that your distance from the center is not going to change. So you are always at a certain constant distance from the center. That is how, or that is why, you have also defined the trajectory, which is a circle. So that's why it's a circular motion. Secondly, the uniform part, okay? So the uniform part makes sure that you are covering equal amount of distance in equal amount of time. Basically saying that your speed is not changing. So if you look at the length of these arrows, the green lines that you're seeing here, we're going to see that these lengths are not changing from one place to another. Basically saying that the speed is constant. And we can also find the velocity, the speed very easily by just reminding ourselves the circumference of the circle. The circumference is 2 pi r. If we know the radius, we know the total length of this line, this circular line that we have drawn, or basically the path. And then once we know the length of the trajectory, if we divide it with time, right? Distance over time is speed. So we can easily find the speed. But what we can notice here is quite interesting, is that this is a classic case where you have the velocity changing from point to point without changing the speed. Remember when we talked about velocity changes or acceleration, we talked about two cases. In one case, you have magnitudes changing. In the second case, you have the direction changing, keeping the magnitude constant. In this case, you have the magnitude staying the same. However, the direction of the velocity is changing at each and every point, basically giving you an acceleration. So if I have to draw, and for each of these points, the velocity, by the way, is along the tangent. So if you want to draw the velocity vector at this point, you will just have to draw a tangent and you'll just have to point the arrow according to the way this guy is moving, right? So it's going anti-clockwise. So your arrow should look at this point like this. And it will, of course, have the same length as these guys, which I did not draw. That's my bad. But maybe I should do this. But most importantly, also, it will give you a new direction from what it was giving you here, okay? So at each and every point, basically, what you are getting is a new velocity. When velocities change from one point to another, we call, or we say that there is an acceleration. And that's exactly what we have here. We have an accelerated motion, even though there is no change of speed. But before we go into details of that acceleration, we need more tools in our toolbox. We need a lot more conventional tools, okay, that will allow us to describe rotational motion or circular motion. So the standard circular motion description tools are basically the arc length, okay? So S equals to r theta is a very first and standard relation, which you might have already seen if you worked with, in pre-calculus, if you worked with radians or how radians were defined. So I want you guys to pay attention, or special attention, to this relation, okay? So when an object travels in a complete circle, right? And let's say this is a circle, all right? When this object starts from here, goes all the way and comes back here, it made one complete revolution. One complete revolution is basically 360-degree angle. In angular way, you are going to say that this particle has traveled 360 degrees. In another unit, you can say that this particle has traveled 2 pi radian. So 2 pi radian is nothing but similar to 360 degree. It's just another angle. It's just kilograms and pounds, or centimeters and inches, okay? But it's extremely important for us to understand when to use radians and when to use degrees. In certain formula in certain equations, especially in simple harmonic motion when you are going to learn it at the very end of this semester. You will start using radians. And also in rotational motion or circular motion problems, you are going to use radians a lot, pretty much all the time. In certain other cases, you're going to use degrees, or like, for example, in projectile motion, you have used degrees. So make sure that you remember or you understand or you write it down when you write an equation. An equation that involves theta should always tell you, or you should write down besides it, that if you are working with radians or degrees. Generally, when you put theta somewhere, you imagine or you kind of assume that it's in degrees. But in certain cases, it could be in radians. So if you do not use the correct unit, you're going to end up having very weird calculations, and sometimes, or probably all the time, you're going to get wrong results, okay? So this is the very first relation, and this is a relationship between the length. So S is basically the length of this line. Imagine if you took this line, if this is a chord, right? And imagine if you draw that line as a straight line, right? Like this, and then you measure it, how long it is, using a meter stick. What you're going to get is basically this S. R is, of course, the radius of the path. Because this is a circle, there will always be a radius. Whatever the radius is, you are expressing it right here. And it has the same unit as S, okay? So they will both have meters or centimeters or millimeters, something like that. And that's why theta is in radian. And in radian, you are not specifying any like length unit. So the length unit cancels. What you are seeing here is basically an angle as a ratio, okay? So with that, I'm going to move forward, and we're going to learn about our next topics. And this is basically, once we know the initial and final positions, this is the same as linear motion, right? Imagine your particle was at theta I. The angle, initial angle was theta I at t equals to ti, or the initial time. At a later time, your object is right here, right? So it moved from here to here along this line, excuse me. And now you have a new time, tf, which is ti plus delta t. So you can simply use delta t to be tf minus ti. As always, there is nothing new there. But it has moved to a new angle, right? So this new angle is theta f. And just like your x and y direction, you can find angular displacement to be equals to delta theta, theta f minus theta I. Always subtract initial from final and you get the displacement, or you get the angular displacement in this case. So once you know the angular displacement and the time interval, you can find out angular velocity. And this is, again, average angular velocity. And once you know the average quantity, you can follow the footsteps of instantaneous velocity definition that you already learned during your past lessons, right? And now you suddenly will also have an instantaneous angular velocity, okay? So this is an instantaneous angular velocity. This is d theta dt. And again, you found that by making this time interval extremely small, infinitesimally small. And all the previous kinematics equations are going to be similar, okay? So if you have a uniform circular motion, you can say that theta f, or the final position, final angular position, is equals to the initial angular position plus constant speed, constant angular speed times delta t. And this should remind you about a similar expression you found out, right? xf equals to xi plus v times delta t. And that you already have learned and you solved problems with. And you're just seeing the angular version of it. Instead of X and Y, you are working with angles now. And also, when angular velocity is constant, this is uniform circular motion, we have talked about it. When you have delta theta is 2 pi, basically saying if you start moving, if this is your center, this is the radius, and if you start from here, and if you go all the way and come back, you have made one complete revolution. One complete revolution is 2 pi. And if you were moving with constant velocity, then the time taken in doing this is 2 pi over omega, right? And that 2 pi over omega is nothing but time period, the time required to travel one complete revolution. I think we are going to stop here because we need to go into the discussion of our much awaited accelerations. So I'm going to stop and then we will come back and start discussing the acceleration and how the two mutually perpendicular acceleration components make the circular motion so special. So I'm going to stop here. And then we are going to meet again for the last and fourth segment of chapter 4 discussions.